Okay, for those joining, watching afterwards, we just did a summary of the new homework assignments posted to Canvas. We have a field trip summary coming up after our class field trips are done, due on November 11th, a brief writing assignment, maybe 2 pages, and then the soil moisture regime, soil temperature regimes activity using the provided data to do a little analysis and interpretation of soil climate data here. The instructions and the data that you're supposed to use are posted here. And these are both assigned to the students here in Moscow and our CSI students that join virtually. CSI students will not be able to write about our Moscow field trips. Instead, you will have your own field trip destinations to synthesize and summarize. With that, we are going to go back to our soil moisture and temperature regime slides. We went through this kind of quickly at the start or at the end of last Thursday's meeting. We talked about the gradients of soil moisture regimes and really like the amount of moisture available in soils. We have a lot more soil moisture in the eastern US, the green and the blue zones. Green is the eutic, blue is the aqueic moisture regime. And from the east to the Midwest to like the Great Plains, a lot of the moisture status or the moisture availability is determined by just how far east to west you are on a gradient of longitude. Once we get into the western US, the moisture and the climate wetness isn't really indicated by the longitude so much as it is by the elevation. So as you increase in elevation in the west, you get a little more precipitation usually, and we find the aritic and the xeric are the drier side. And then your precipitation, we can get into the eutic moisture again on the coast and in the high elevation in Idaho, not because of where we are gradient wise, but because we're east to west gradient, but a low to high elevation gradient. So this was our summary table that where we left off on. A couple notes I have for this one are, this is evaluated when like the official definitions are always evaluated on for a normal year. What does it mean to be a normal year? Well, within one standard deviation of the last 30 years of climate data. 30 years updated, like that. When you talk about meteorology and climatology, it's normal years are always based on like a 30-year increment that updates every 10 years. So that's just a little bit what it means for the determinations. Changing the moisture regime and the temperature regime is possible long-term, but not really on a yearly basis. So just because you have a particularly wet year, a particularly dry year, doesn't mean you can go reclassify all the soil series in your area. Potentially really change the classification, but that's not possible to do just on 1 year of weather alone. It has to be the climate conditions, right? But it's possible some of these have actually changed since maybe they were first mapped. So I know a grad student that was kind of split between soils and forestry a couple of years ago did a research project that was pretty much all about measuring the moisture and the precipitation and the water availability of different parts of a soil profile in a bunch of different places to kind of verify. These are all mapped as a xeric moisture regime, but can we verify that, or do we need to update the way that the climate regimes, the moisture and temperature are kind of distributed across the Western US? And I think our findings were that it was really hard to do this, to get good quality data at many different depths of a soil profile for like the moisture and the temperature, for example. But also the data she was able to use to conclude moisture temperature regime information is that maybe it doesn't always match. Maybe we're not necessarily xeric everywhere in the West across Montana and Oregon and Idaho, but it's kind of hard to get a handle on. It's hard to just understand based on the definitions alone what all these mean. So that's why I have the main idea up there too. What's most important to me is that you know the main idea of these moisture regimes, maybe where to find them too. That is what I recommend, but also this aritic and the toric here at the very end. If I didn't mention before, they pretty much mean the same thing. They're just used in different categories of soil taxonomy. The root words of these both come from aritic and toric, mean dry for aritic and both hot and dry for toric, even though aritic moisture regimes are usually pretty hot as well. So those are are practically interchangeable. When we talk about Utica gets wet year round, Xeric has a dry summer, wet winter, Utica has a very dry soil. What does it really mean to be wet and dry for a soil profile? Well, it has to do with the moisture tension in the soil as we measure it in the kilopascals. Is this idea, or is this number specifically 1500 kilopascals familiar to anybody from maybe intro soils? Verity, maybe?
Soil physics.
You got soil physics, of course, yes. Robert Heinz teaches soil physics as well as soil 205, of course. He's probably mentioned this number 1500 kilopascals before. This is the permanent wilting point for plants. It's when the amount of water in a soil profile is no longer enough to like sustain plant life. Maybe there is water in the soil profile, but it's not going to be available to plants because of how tightly retained it is to the soil, individual soil particles. The demonstration I like to give always in soil 206 lab, I'm not sure if that continued afterwards, but you imagine a sponge that's totally saturated and like water's dripping out of it. That would be a sponge or soil profile in its saturated condition. As soon as it drains out due to gravity, so where it's not dripping anymore, but it's still full of water, that's the soil field capacity, the maximum amount of water the soil profile can store kind of on its own. As you start to wring out the sponge, that you're like a plant extracting water from it, all the water that's available, until the point where no more water can be wrung out of the sponge, but you can still feel the moisture and it still feels kind of wet. It's not a bone dry sponge necessarily. At the point where you can't squeeze any more water out of it, that would be the equivalent of 1500 kilopascals for a plant, the permanent wilting point. If you let the sponge air dry for a long time, eventually it will shrink, shrivel up, and be totally dry. That'd be like putting soil in the oven to dry it. But permanent wilting point is our definition for soil moisture and temperature regime, or at least moisture status indicator of what's dry soil, what won't be able to support any plant growth. So no water is available to plants at this kind of dry definition. So if you start to put this dryness, this wetness, the precipitation that kind of indicates this in terms of well, we got our plant usage here and also evapotranspiration, thinking of it like a supply and a demand almost, and also how it changes throughout the year, you can start to put together this water balance or this water budget for a soil profile across the year. And this is what our homework is going to kind of dive into here. But we have 4 different stages of this water balance, starting with that stage where we're wringing the water out of the sponge, where we have moisture in the soil above the permanent wilting point, which means the water is available to plants. We call that utilization, abbreviated with a U. Plants are able to utilize the water that's stored in the soil profile. Plants are using that water all the way until there's no more of it, until there's a deficit where we reach that permanent wilting point. Plant demand will exceed the plant available water. We have a higher demand for water than we have a supply. We usually reach a deficit around here in the summer when the soil gets dry or like too dry to support plant growth. Eventually, things turn around. We start to get a little more rain in the system. We start to recharge where maybe evapotranspiration has decreased. The demand is decreased and the supply is increasing again. We're recharging the amount of water in the soil profile. We're increasing up to the field capacity until the point where we reach that capacity, or maybe we keep accumulating more water. There's more and more rain, maybe in a really wet winter, until we have a surplus. More moisture than can be stored in the soil is what the water balance is at now. So we have these 4 stages. Eventually you go from surplus when maybe precipitation starts to decrease a little bit, or at least plant activity increases and you have the evapotranspiration demand restored to the soil profile. You start to utilize the water that's available then until it cycles all the way through. So what does this look like? Our representation of this, at least starting with the Utic soil moisture regime. So we're looking at the solid line here in the middle that raises in the summer. That's our evapotranspiration. So the amount of plant demand for the water is highest in the summer during the growing season. The dashed line is our precipitation. So while this looks like it's more in the winter, less in the summer, keep in mind that precipitation in inches here has a minimum in August and September of 2 inches per month. That's still quite a bit of rain. The average through the year, I would probably put here in the middle at 3.5 or 4 inches of rain per month all year. That's quite a bit. So there's never too much deficit. This is our eudictic soil moisture regime. Starting with utilization in the summer where we have a lot of plant demand, but still a lot of water in the soil profile to meet it. As soon as we reach 0 plant available water, 1,500 kilopascals water retention, we hit the deficit, which is quickly met with the recharge. So as soon as precipitation is increasing above, yes, we can see that there. Precipitation increases above the evapotranspiration, so the lines cross here. The dashed line goes above the solid line of demand. We have the recharge until our soil moisture control section, at least the range where we consider the capacity of the moisture is full again. We consider full to be 75 equivalent centimeters of water. I think that is. Just to put a number on it. So that's explained more in the activity directions when you're actually working through it. But once we reach the maximum, it's at a surplus. Surplus is going to continue all winter until the evapotranspiration demand increases above the supply, which is the dashed line. We're back into the utilization. The eustic, on the other hand, slightly different, where we have dashed line is precipitation once again, more in the summer than the winter here that kind of match our plant demand. We have just utilization and recharge really. We have, or it goes to deficit. Yes, that's right. So the really high plant demand is eventually going to remove all available water from our utilization. Utilization continues until whenever the moisture is drained out of the soil profile. We're in deficit mostly, and then the lines cross again. Our supply exceeds our demand. The dashed line goes above. We are in recharge, and this one never really hits a surplus because there's just not enough supply of precipitation during the winter while plant demand is low to reach a surplus. So you never actually go through the fourth stage of surplus. We stay in utilization and deficit for most of the year. This would be like the Great Plains, Oklahoma City, for example, with the eustic moisture regime. Closer to home now is Xeric. This one looks a little bit different. Our potential evapotranspiration is the green one here, this curving line right there. That is highest in the summer along with the temperature, which are the dots there. We're not really considering temperature for our moisture regime, but our precipitation line is the triangles, which is this kind of U-shaped one right there. So this one is, we have utilization in the summer and then split between deficit, quite a bit of recharge, and then a lot of surplus in the winter where we have way more precipitation than evapotranspiration in the winter. So precipitation gets really low. This is down to this is maybe 10 millimeters in the summer months. Just a fraction, merely a fraction of an inch available there. So this is familiar what we have here. Portland, also other places in the Northwest, could be the xeric moisture regime. And then aritic would be the last one. A lot of deficit there is what most of the figure here shows. Evapotranspiration is very high compared to the precipitation very low, maybe an inch of rain at the most in any given year. There's still a little bit, there's utilization, there's plants growing with some amount of water that's available, but not that much. Instead, it spends most of the year in deficit. And there's a little bit of recharge in maybe November, December, January, when evapotranspiration is low and they get just a little bit of rain. This is the example data from Phoenix, Arizona. I mentioned before, my sister lives in Phoenix. I've been to visit the last couple Decembers in Phoenix, and fly down to Arizona. I think it's going to be really nice, really warm weather in December. And just my luck is that they're getting their 1 inch of rain right there, right then when I'm visiting. But even if it's 50 degrees in December in Phoenix, that feels pretty good too. Questions? Okay, yeah, no surplus. Like the Ustic, there's just not enough total precipitation to fully recharge our soil moisture. Questions about the water balance, the water budgets, the soil moisture regimes. That's only half of it. We also have the temperature regimes to consider. We can consider temperature on a gradient as well. Instead of east to west, though, we're kind of on a north-south gradient now for soil temperatures in the US. This is maybe familiar to think about if you've looked at plant or like garden suitability zones across the US. A lot of like gardening or landscaping plants are evaluated by their suitability for temperatures, which is this north to south gradient rather than east to west. Once again, it's elevation in the western US that really determines the temperature. So the nice gradient on the eastern part of the US kind of goes away here because of the much more variable terrain. And we have a similar schemes, so similar table to set up to go through the soil temperature regime, starting with mean annual temperatures at 50 centimeters deep in the soil. So rather than the amount of precipitation that we get at the surface, instead we're evaluating about 2 feet down in the soil profile, a little less, what is the temperature throughout the year, and we're doing this in Celsius. Starting off with a generally cold one, we have our cryic temperature regime. The range for what the average annual soil temperature is at this depth of the profile, it's between 0 to 8 degrees Celsius. So we know 0 is freezing at 32 degrees Fahrenheit. 8 degrees Celsius is like upper 40s for an average soil temperature, and the seasonal difference is less than 6 degrees Celsius. The main idea here is that it's cold all the time. So this isn't really to say that the soil stays frozen all year. That would be a different temperature regime, but our like below the surface temperature stays pretty cool. Cultivation suitability, what can grow here? Usually it's only trees and forestry kind of cultivation, silviculture land use. You could find a cryic temperature regime, maybe up in the Selkirks, maybe over in the Cascades, kind of higher elevation places around here at least. So it doesn't need to be 40 degrees like air temperature all year. We're talking about the soil again. So things that can keep the soil temperature pretty low, especially with the seasonal difference, where it doesn't change much throughout the year, would be if there's a snowpack that stays on the surface maybe into May or June, that'll keep the soil temperature pretty low, understandably. But also, if there's a lot of trees, and if we're usually in forests, trees are going to shade the soil surface pretty well, keep it well insulated, keep the seasonal difference changing less than 6 degrees at depth from the summer to the winter. So the air temperature could be up in the 70s or warmer maybe in these places, but the soil temperature is going to stay pretty cold all the time. Frigid, on the other hand, is the same temperature range of 0 to 8 degrees Celsius, but the seasonal difference can be over 6 degrees Celsius now. So where we're not as insulated, where it gets maybe a little bit warmer in the summer, we still have cold winters, but maybe warm summers, maybe a little less insulation. We're in the frigid temperature regime. This would be small grains. You could any agriculture here would be like oats, barley, rye cultivation. Location locally, Moscow Mountain at least, where we have this temperature condition, but North Dakota, Maine, other kind of the northern extents across the US would be in the frigid temperature regime kind of by default. Cold in the winter still, but it warms up a little in the summer. We have a more change over the course of the year for temperature. Our mesic temperature regime, this one should be familiar. That's where most of our soil pit field trips have been and what we have on the Palouse. The mean average soil temperature between 8 and 15 degrees Celsius. We're kind of on the cold side on the Palouse. We're kind of on the low end of that because of our cool winters. But in general, warmer summers. So we're just increasing the average temperature a little bit. Here you have a lot more flexibility for cultivation based on temperature alone. Could be corn, soybeans, wheat. And perhaps unsurprising, this is our Palouse and most of the Midwest temperature regime, Iowa, maybe Kentucky. I think it's the yellow color on our on the map. On the last slide, mesic temperature increasing a little bit more as the soil gets warmer and warmer. We're into the thermic. It starts to sound pretty hot. Average temperature in a thermic regime is 15 to 22 degrees Celsius. In order for that to be the average temperature throughout the year, you really can't get very cold in the winter. So at best you have mild winters and pretty hot summers. Good for growing probably drier, probably just hotter temperature crops, cotton and sorghum, for example. And you would find a thermic regime in Mississippi, South Carolina, Texas, or California, maybe. Definitely warmer places. Now we finish out with the vacation destinations in the hyperthermic temperature regime. For your average temperature to be over 22 degrees Celsius all year, you have to be pretty hot all year. Hot all the time. Really, citrus fruits are the main crop that I think of for these really warm places. This would be just the very southern extent of Texas, southern Florida, Miami, Tampa, hyperthermic. Just like cryic and frigid have the same temperature range, just seasonal difference. To distinguish them, there's hyperthermic and isohyperthermic. You might see that on occasion. To be isohyperthermic, all that means is the average temperature stays very constant. So it's possible you could be either hot all the time or maybe get a little, you could have warm winters and extremely hot summers and still be hyperthermic. If you stay like in the tropical places, maybe near the equator that stay pretty much the same temperature all year, that's how you get the isohyperthermic temperature regime. I mentioned before, if the mean annual soil temperature is below 0 degrees Celsius, that means you're frozen all year. When you have permanently frozen soil, that's a permafrost. That's like our gelosol soil order. We would call that the gelic temperature regime. But in order to see or consider a gelic temperature regime, that would have to be our Alaska field trip. Unfortunately, bucket list item to see a gelic temperature regime. Not gonna happen for us this semester, but frigid and mesic, I think, are the two most important ones for us to know. How are you supposed to know in the first place, though, if you're going to a soil pit or describing a location once, if you're going to do that one time, how are you supposed to know what the temperature is all year? Well, that's wouldn't it be great if you can use, how about you use something that actually is there all year as a reference? So for North Central Idaho, at least the NRCS has this example for this, it's like a dichotomous key to relate the vegetation or the kind of plant communities that are in a given location to the climate conditions, so the temperature and the moisture regime. If you can identify a subalpine fir and a mountain hemlock, then you know, based on the conditions that it takes to grow these trees or their climate suitability, they're usually high elevation where it's usually cold. That's evidence of a cryic temperature regime. the Udic moisture regime if you have subalpine fir. And then working through the list, if you have grand fir present, you're probably in the frigid temperature regime in either the Udic or the xeric based on some of the other understory plants that might be present. Doug fir, ponderosa pine's not on here. That's also one of the drier ones. How you can kind of figure this out unless, if you don't already know, if you don't have climate data available or something, you can always check Web Soil Survey to see what the example or the nominal, like the mapped as soil series is for an area. That can indicate temperature regime or moisture regime for your taxonomic classification for your project pits specifically is what I'm thinking of. Or you can have, if you can find one of these flowchart resources to figure out what the temperature conditions are, that can be helpful too. Any questions about climate or specifically how we're considering climate for soil classification purposes? With about 20 minutes left, I'm going to switch to our next set of slides here. We've been working through, we know our overall goal is like the soil taxonomy. Now speaking the language of soil taxonomy, we make a few different generalizations in soil taxonomy to assign like our classification groups to soil profiles. And one of these is, one of the major ones of this is the epipedon. So probably a new word, pedon would be familiar. Epi, though, maybe also a familiar prefix meaning like surface or the top, the outside. Epipedon really just means the surface layer of the soil. What we consider the surface layer, or by definition, at least what it means to be a surface or an epipedon, is that it's darkened by organic matter, or it can show evidence of eluviation, or probably both. Darkened by organic matter is generally the giveaway for what the epipedon is. Broadly, you can think of this as topsoil as opposed to the subsoil. Let's say we brought somebody into a soil pit who had no prior experience with soil or understanding of horizons or soil classification, and we asked them to draw one line, say where's the topsoil and where's the subsoil. I think it's pretty likely that a line that they draw would be pretty close to the line of the epipedon versus the subsurface. Generally speaking, the topsoil, but it's not important to recognize that it's not just the first horizon. If you have multiple A horizons in a soil profile, those would all be considered in the epipedon. It could be like an AP and an A horizon, or an A1, A2, maybe AB transition. That would also be likely part of the epipedon. It's also possible that you can even have a B horizon be part of the epipedon if this organic matter darkening, this melanization process, is continuing into or through the B horizon. So usually this would be like, I would lean towards saying an AB horizon in the first place if we have the structure of a B horizon but the color of an A horizon. That's really the only criteria I use to say AB transition. But if you already have AB transition and the color's a little bit lighter, but it's still kind of darkened by the organic matter. Once again, in the subjectivity, now a matter of opinion, what horizon goes with what. But it's possible to have maybe a BW horizon count as the epipedon, not just the first horizon that you describe. It's the kind of the generalized a grouping of what the general surface horizons are. Speaking of grouping, we're going to group all the epipedons really into 8 total options. So there's 8 total options for the whole entire, the book on soil taxonomy for all the soils in the whole entire world. For as diverse as those are, we really only have 8 different epipedons to choose from. Starting with our favorite, the most relevant, the one that we've seen the most so far, is the Moloch epipedon. This one matches really well with grasslands or prairies, or at least historic grasslands and prairies, what the soil development conditions were like. There are a lot of diverse criteria for what exactly it means to be a malic epipedon, but we can really condense them down into 4 main criteria. And that's the depth. They have to be deep epipedons, about 25 centimeters deep. It's possible that special cases can make them shallower if you have a malic epipedon or these A horizons maybe directly over bedrock. R horizon, you don't have to be quite necessarily 25 centimeters deep, or if there's a root limiting layer like a durapan or a fragipan or something pretty shallow in the profile, then it's allowed to be a little bit less than 25 centimeters. Usually 18 is the cutoff, though. At least 18 centimeters deep for a malic epipedon. Most cases, though, without a root limiting layer or anything in the soil profile, 25 centimeters is the number to remember. So they have to be deep, they have to be dark, 10 YR 3.3 value chroma or darker. So this is really isolating the bottom left corner of any given color page in the one cell color book, 3.3 value chroma or darker when it's the moist color. The dry color can be a little bit higher, value. So like 5, I think, 5.3 or so is the dry color cutoff. But moist color is the one to remember. The base saturation has to be over 50%. So this is maybe a soil fertility idea, but the amount of base cations, so the exchangeable positively charged elements that usually are of most interest for like plant growth, plant root uptake, the calciums, magnesiums, potassium, sodium, these base cations, what percent of the total cation exchange capacity is occupied by these specific cations? If that's over 50%, we qualify as the malic epipedon. This is usually not a key cutoff for the Palouse soils, but maybe it's an increasing concern where we have really high soil acidification going on. Could be a agricultural issue or a land management issue for the Palouse. As acidity increases, pH is decreasing, the amount of concentration of H plus ions in solution and in the soil is increasing. There's going to be a higher proportion of these H pluses on cation exchange sites, which do not count as one of the base cations. So as the amount of H plus is increasing in soil, this base saturation number is going to start to decrease. And usually we don't get to 50%. That would be pretty low. But in areas that are more acidic, it's possible that base saturation is going to drop below 50% and you'll no longer be a mollisol. The fourth main criteria is that at least 0.6% organic carbon. We very easily meet this in the topsoil of the Palouse. The technical rule here is that it has to be at least 0.6% organic carbon more than whatever's in the C horizon. So if you somehow have really organic rich C horizon paramaterial, you have to have more carbon than that in the A horizons in the epipedon. But most of the time, 0.6 works as the cutoff for the topsoil. So when you meet those 4, almost always it'll be a malic epipedon. There are some other, I think there's 8 or 9 or 10 maybe official criteria of the malic epipedon, but nobody ever taught them to me, and I really can find no. I really struggle to see how they're ever make or break for the malic epipedon, and something about an N value coefficient, something about a physical, like a fluidity value or something, nothing practical that you'd ever use. And I just kind of not very proud, but just ignore it and push it to the side and focus on these 4 main criteria whenever I talk about malic epipedons and teach class. It was only just a couple of years ago at the Soil Science Society of America conference, one of the most prominent pedologists and soil judging coaches out there stood up and gave a presentation of a proposal to simplify the malic epipedon requirements, because we have all these other categories that nobody ever uses and nobody ever understands why we even do it. And that was very validating for me. I thought I was missing something because I didn't understand what a fluidity value meant for a malic epipedon. Turns out everybody maybe agrees. But these are the 4 to know for the malic epipedon. Let's say we talked about that base saturation though. You have to meet all 4 of these criteria. If you're not meeting one, you're not a molic epipedon. What if you happen to drop below 50% base saturation, but you keep everything else the same? That would be our umbric epipedon. It's the same depth, the same color, the same organic matter requirements as molic, and the only difference is base saturation is under 50%. So these are really common. You could probably find them somewhere in Idaho. Extremely common in the southeast U.S., a place with just lower base saturation on the whole. This would be the Ultasol soil order, but it's like the molic epipedon for these highly weathered, low base saturation soils. Umbric epipedon. Our soil dredging team was just in Wisconsin, and we ended up seeing a lot more of these umbric epipedons than we expected there. I think it's because of like the pH. They have a lot of acidic forest soils in general, more rain over there than we do here. A little different like land management and land use than the Palouse, but sometimes their base saturation would drop under 50%, and then that would reclassify a lot of soil profiles into the umbric epipedon and change the taxonomy of them. Anywhere base saturation is generally low. In our part of the world, it's pretty safe to assume that the base saturation is over 50%.
Did you just do this by just pH in your soil? That's how you just determine, like, how do you determine?
How to actually determine base saturation? That's a good question. I think pH is a good indicator. That's what a lot of soil characterization would be. If you need to know the base saturation, I think the official way to do it is, I think you might need like an ICP, like a lot of lab work to actually analyze the elemental concentrations. I never had to actually do base saturation, something I think we should probably be doing more of as soil scientists and at the U of I, but that's a good question. Molic and umbric. Next, we are into a little different one, going a different direction with the anthropic epipedon. This is a human-altered and human-transported materials epipedon. Kind of artificial material, or maybe disturbed area. Could be mine tailings, could be dredged material, non-litter artifacts. So just because we might have, we might have like human-influenced landscapes, constructed features on the landscape, artifacts. This picture in the top right these are like shells that were brought. This is a midden, it's called. I think it's a like a indigenous cultural resource where shells were brought and maybe used and disposed of. I don't have a great understanding, but a midden counts as an anthropic epipedon, as well as locations with other kinds of artifacts. We can usually recognize this with a high phosphorus content, could be from food debris, compost, or manure or something. It does not count if you have like fertilizer or tillage disturbance. So just because you might have human-altered materials from long-term plowing and you're adding fertilizer and you have an AP horizon, that does not count as anthropic. It has to be either a caret A for like transported materials, caret C at the top too probably would work, or perhaps a U subordinate distinction would be good places to recognize the anthropic epipedon. Not super likely to find by accident, I would say. If you're out digging a soil profile, chances are you're looking for something like this, or you're looking in an area that is disturbed before. And there's a depth requirement on this too, like we saw at Cook Farm last week. Maybe if a little bit of soil from the bottom of the profile somehow gets transported to the top, that could technically fit our definition of human transported materials. But I think the depth is probably around 50 centimeters on this. You don't have to know that, but if there's just 10 centimeters on the top or so, that is probably not enough to change what the epipedon is. Another Human influenced one, human influenced epipedon to consider is called the Plagan epipedon. Plagan is also human influenced. It's represented by a thick, dark mineral layer produced by long-term manure applications. And when we talk about long-term here, we're talking hundreds to thousands of years of manure application, probably. May contain artifacts or spade marks. I think these kind of like slashes or dark streaks at the bottom are described as like spade marks in the soil profile. Could contain artifacts because of artificial influence here, but the history of agriculture and of long-term manure applications has to be so long that it's more on like a European time scale of agriculture rather than the US. Although we might have a 200 plus year history of agriculture in the US, that's not long enough to form one of these mineral plagan, really dark, really organic topsoil epipedons, as we call them. Kind of a unique European soil feature, but it still gets its own description of epipedon. Another pretty organic one that we are likely to see here, if it's only organic material, you can have the folistic and the histic epipedons. These are both O horizons with a depth of at least 20 centimeters. Folistic is a dry organic epipedon. It can be saturated as long as it's less than 30 total days per year. Holistic epipedon, an example of this is from a soil development study that a PhD student here at the U of I did maybe 20 years ago at Craters of the Moon, a really young, kind of recent landscape to study soil development on. And some of the first soil horizon to develop probably out of this basalt R horizon would be an O horizon of organic material from some of these these plants that are able to grow and colonize the landscape. Once enough organic material is there to put down and be an O horizon, it's going to stay pretty dry and technically be a holistic epipedon, as opposed to the more traditional organic epipedon that we might be more likely to find here as a histic epipedon, where it's generally wet, saturated at least 30 total days per year. That's the one when we usually think of like a wetland or a histosol soil order. We're talking about a histic epipedon. Just because you might have an O horizon at the surface doesn't mean you go right to the histic epipedon, because epipedons aren't only talking about the first horizon that you describe. You only would say it's a histic epipedon if there's 20 total centimeters of O horizon. That's quite a lot. I don't think a normal like forest litter layer would ever get to 20 centimeters thick, for example. With 2 to go in our remaining time here, melanic epipedon. This is another very unique one. It's a thick, dark surface formed from volcanic ash. So we know we have volcanic ash. We have andisols around here in North Idaho, but we usually don't see these melanic epipedons, unfortunately. Melanic epipedons require these andic soil properties throughout. This is like a diagnostic soil feature that we will talk more about soon in lecture. But what does it mean to have an andic soil or to have these andic soil properties? It's a low bulk density because we know the volcanic ash is really light and loose. A high phosphate retention. So this is going to require a little lab work to find out too. The phosphorus retention is really high in these andic soils, as well as the aluminum and iron content. So the mineralogy of the volcanic ash, volcanic tephra, whatever sediment derives from a volcanic eruption might have high aluminum and iron content to be an andic soil property. It needs a dark color, even darker than the molic epipedon does. 2.5, 2 or less for the value in the chroma. This is like really black soil. Where the molic epipedon needed 0.6% organic carbon or more, melanic epipedons need 6.0% organic carbon or more as an average, and at least 4% in all parts of the Smolanic epipedon. And then it needs 30 or more centimeters within a thickness of 40 centimeters. So all these caveats, well, it could be as low as this, or you can have 10 centimeters in the top 40 that don't meet it, is to account for, well, you have a volcanic eruption and then a soil profile of some other parent material developing out of it maybe, and then another volcanic eruption if you're probably really close to the volcanoes. So this is more common. You can maybe have some of these in Western Washington, but in like Japan, the Ring of Fire, kind of on these active volcanoes, Costa Rica too has melanic epipedons. Would be where you find that. Ochric epipedons then is the 8th of our 8 options. The definition of this one is just everything else. So we went through all the more restrictive definitions. Any other soil that you find, if it doesn't meet the molic, it doesn't meet Histic is on O horizon, it's a natural soil profile, right? Not anthropic. Chances are it's going to be ochric. And that'll do it for us today. Thank you, everybody. Let me know if you have questions on anything on campus.
Anymore, I think that